This is section 11.6, Polar Equations and Graphs. We're going to start with this new coordinate system. Polar equations and graphs are in a whole new type of graphing system. In this system, instead of an origin, you have something called the pole, which acts like the origin, but it's called the pole. And you have a polar axis, which extends only to the right. And it's like the positive x-axis. And any point that we have in this system has coordinates r, theta. So to contrast that with what we already are familiar with, we're used to having two axes, which are full lines going to positive and negative infinity each. And to find the location of any point in this system, the rectangular system, by the way, this is called a rectangular system because if I had a complete grid, the grid would be formed of rectangles. Ideally, we want those rectangles to be squares. If they're not square, then the graph is distorted. But anyway, it's called a rectangular system, and it uses points that are ordered pairs in the form x, y. And of course, as you know, what x, y means is that for the first coordinate, you move left or right to the appropriate place on that number line. So for example, I wanted you to graph 2, -3. You would move to the 2 on x-axis and -3 on the y-axis and find out where those intersect, which is right there. So this is all about horizontal movement and vertical movement in this system. In the polar system, we're going to be rotating about the polar axis, or from the polar axis, counterclockwise for positive theta. So this is familiar. It's what we expect. And then we're going to go out along that ray a distance of some amount. And so let's say it's at 3 or something. Then that point would be located by how far the angle has rotated around from the polar axis and how far the point is from the pole. That's what r represents. Okay, so what is the connection between these two? Because you could very easily see the pole placed over the origin and the polar axis over the x-axis, and that you could actually have points and be trying to find their polar coordinates or their rectangular coordinates and vice versa, being able to convert between the two. So if we were to do that, we need to realize that in order to relate those four variables to each other, x and y related to r and theta, we could draw a rectangular grid here and put on the positive x-axis the polar axis. So that was the pole that I put at the origin, and this is the polar axis. And if we were to move to, say, this angle here from the polar axis, so we'll go theta, and we were to move out along that to some point and stop, say, that far out at that point right there where the arrow ends. Make a great big dot there so you can see where I'm going. So that dot there. Then the relationship that we would have is that shouldn't have drawn that arc where I did. Should have drawn it smaller. Oh well. This is x. This is y. And of course, theta is that arc that I kind of drew over. And r is the length of this pink segment that goes from the pole to the point. And the relationship amongst these is really important to be able to convert between them. So we need an equation that would relate, say, x and y to r. Well, we already have an equation for that. R squared, because it's a right triangle, is x squared plus y squared. And so this equation would let you take an xy pair and find the radius for the polar coordinates. So this will be useful in going from rectangular to polar. While we're talking about that, the other part of the polar coordinate is the angle theta. And so how are x and y related to theta? Well, that would be by the trigonometric definition of tangent of theta, y over x. So with this equation, if you know y and x, you could find theta. Now, if you want to go from polar to rectangular, you're going to have equations that, given r and theta, would let you find x, or given r and theta, would let you find y. So if you think about it, the relationship between theta and x and r, if you look at that right triangle, they're related by cosine of theta, being x over r. And what relates y, r, and theta to each other? That would be sine of theta. Of course, that's... Why did I write y there? I'm sorry. I think I was already thinking ahead to the thing I was going to write for sine of theta and just lost my head for a second. So I apologize. Okay, so that's x over r. And sine of theta is y over r. And so if we solve the first equation for x by multiplying both sides by r, we get x equals r cosine theta. And doing the same thing to solve for y, multiply both sides by r, you get y equals r sine of theta. And so those are the equations we would use. That if I know r and theta, this equation would help me find x. And if I know r and theta, this equation would let me find y. Okay. So to be able to go back and forth between these, I'd like to practice that a little bit. So let's say that we have polar coordinates for a point P, and those polar coordinates are 2 30 degrees. And I want to know, what are the rectangular coordinates? Well, of course, that means that r is 2 and theta is 30 degrees. By the way, theta can be measured in degrees or radians. They're both used at different times, so get used to that. All right, so we're going from polar to rectangular, so I'm going to use the two equations on the right side. So x will be r cosine of theta, and cosine of 30 degrees is square root of 3 over 2, which simplifies to be square root of 3. And y will be r, which is 2, sine of theta, which is 30 degrees. The sine of 30 degrees is 1/2. And of course, 2 times 1/2 is 1. And so therefore, the point P in rectangular coordinates would be square root of 3, comma 1. Okay. Now, let me check on something just a second. So the next example I want to work is for point Q. This is example B. Q is a point with coordinates -4, 2 pi over 3. Which of course means that R is -4. Uh-oh, what does that mean? Negative R. We haven't seen negative R. If you recall, when we talked about trigonometry, I said in the trig world, R is positive, and it's always, always, always going to be positive until I change my mind. Or I think I said until polar. So this is what that is. So I think it might take a bit of time to talk about this. It's not extremely difficult, but I do want to mention it before we get very far. So if I have a rectangular grid and a polar grid at the same time, where each mark on the x-axis is the same for the y-axis, this is the set of points that are all 1 away from the pole, a circle. These are the points that are all 2 away from the pole. I'm drawing this as carefully as I can because machine-generated grids like this are better than a hand-drawn grid. But I'm trying to make this one at least look pretty good. And the spacing between the circles should be consistent so that, for example, on the positive x-axis, the first circle is at 1, the second circle is at 2, the third circle is at 3, etc. Okay, that's as much of that as I'm wanting to draw. And a lot of times what you'll see with that are a bunch of line rays, I should say, extending out from the pole. Let me draw some of those in. And these are supposed to be evenly spaced around the circle. And these rays represent major angles that you might want to use. So if you count, I created in the first quadrant 1, 2, 3, 4, 5, 6 regions. 90 degrees divided by 6 would be how much? 15, right. So each one of these represents a movement of 15 degrees. So the first one is 15 degrees, plus 15 is 30 degrees. We might need that one. Plus 15 is 45 degrees, also a good one. The next one would be 60 degrees. And then 75 degrees, and of course 90 degrees at the axis. What if we took the measurement to be in radians? If we took pi over 2 and divided that by 6, that would mean each one of those is worth pi over 12. So 15 degrees would be pi over 12. The next one would be 2 pi over 12, which reduces to pi over 6. Then 3 pi over 12, which reduces to pi over 4. Then 4 pi over 12, which reduces to pi over 3. Then 5 pi over 12. And then 6 pi over 12, which reduces to pi over 2. So 0 here, pi over 12 here, of course. Or, sorry, pi over 2. And I guess I can label the degree versions of those as well. 0 degrees and 90 degrees. And those would actually be in all of the quadrants. This is a pretty typical one. They might draw different radial lines, and it may not look like that. You may have to figure out for yourself how far each one is by taking how many there are from, say, 0 to 9 degrees, and then divide to find out how much each one is worth. But the one I drew is pretty typical. So let's graph this first point that we did. I'm going to put a little pink dot there so you know that one's the one in pink. So I would go, and I know it's in the order R, then 30 degrees, and you can graph it in that order. It's just my thinking process is I'm going to go around to where 30 degrees is and then move out from the pole 2 places. And so that's where that is. And a lot of times if you're putting multiple points on the same grid, you'd want to label that one, say, with the letter P, or the coordinates, but P is shorter, so that's why I'm going to pick that. Let's do the next one in this greenish color, so you can see what I mean by the negative R, because you can have a negative R here. Okay, so I'm going to not draw all of the lines, so I'm going to say that 2 pi over 3 is somewhere about right there. And if I move from the pole along that ray, R will be positive. For R to be negative, I'll have to reverse myself and go into the quadrant over here, 180 degrees away, or pi away from that one. And anything on this ray, when 2 pi over 3 is the angle mentioned, anything on the ray in the 4th quadrant will have a negative R value. So on the 2 pi over 3 ray, since R is negative, I will not go along that ray, but back up and go the other way into the 4th quadrant and out 4. And that point would be right there. And that's Q. Now, I know I have an example I was starting to do, so let me finish it, and then there's something I want to come back to that I probably should have said at the outset. Anyway, knowing R and theta, to find X, I'll take R cosine theta, substituting in the numbers I was given, of course, and Y will be R sine of theta with the appropriate substitutions. The cosine of 2 pi over 3 is negative 1/2. So X will be 2. And sine of 2 pi over 3 is square root of 3 over 2. So that's negative 2 square roots of 3. Therefore, point Q has coordinates 2, comma, negative 2 square roots of 3. So if we look at those coordinates in rectangular, let's go back to P for just a second. Square root of 3 would mean go to the right a little bit more than 1, about 1.7, and then go up 1. And so if you look at that point, you have to imagine the rectangular grid and ignore the circles. But that appears to be just to the left of where 2 is on the x-axis, and it looks to be right in line with where the 1 is on the y-axis. So that seems like a logical answer, and I'm happy with that. Q, let's look at it. If we went to the right 2 and down 2 square roots of 3, does that seem logical that that point would end up there? And that's probably a good thing to do, is check the location. If you were to graph it in polar and rectangular, are you ending up at the same place? That'll save you from accidentally being in the wrong quadrant. So that should help. Now let's go back up here to the top a second. I want to mention something. If you didn't know where that first point was in rectangular that I plotted from the coordinates to negative 3, and I just plotted, well, let's just do a different one. Hold on, let me change my mind. I want to have you do another one. So if I ask you, what are the coordinates of this point right here, a graphed point that I show you, and I ask you to find it, you'd look at it and count left and right so much, up and down so much, and hopefully you would come up with, well, it's negative 1, 2. Well, of course it is. That's exactly right. Now, if you'll look at the answer for Q, if I said, okay, ignore the work over on the left side, and I just plotted that point and asked you, what are the coordinates of that point? Well, for one thing, you could have used degrees instead of radians, but that's not what I'm trying to talk about here. So let's say you're still in radians. What could that be? Well, if I found an angle for an expression of the ray that Q is actually on, that ray, then I could use a positive R. And so Q could be in polar. It could be also for negative pi over 3, for example. Oh my, that's kind of scary, because what that means is that how many different coordinates can any point that's in the polar grid, how many different coordinates are writable for that point? A lot, right? Could I use positive 4 and any angle that's coterminal with negative pi over 3? Yes. Another version of that would be if I were to add 2 pi to negative pi over 3. I'd still be on the same ray, so I'd use a positive R. And there's another version of the coordinates of a point that would be plotted in exactly the same place as Q. And another one I could pick is keep the negative 4, so I'm on the ray in the second quadrant. And instead of using 2 pi over 3, I could either subtract or add 2 pi to be any angle coterminal with that one. And how many coterminal angle representations are there? Infinitely many. And so for that reason, I think I'm going to subtract 2 pi for this one, just to finish that answer. For that reason, a lot of times in the directions for tell me the coordinates of this point in polar, restrictions will be put on you so that there aren't infinitely many correct answers. It'll be like, okay, let's restrict the angle to be only between 0 and 2 pi, and then give me an answer where R is positive, and then maybe also give me an answer where R is negative. And so you'd have to find, a couple of them with very limited options open to you so that there's only one correct answer for each one of those options. Okay, so back to finding the coordinates of points that are given in polar. Find their rectangular versions. Of course, this one, R is 5, and theta it doesn't look like a negative pi over 4. That's what I said, I think, and I didn't think I wrote pi over 4, it just didn't come out. Anyway, theta is negative pi over 4. So, using what we learned, x is equal to r cosine of theta. Y is equal to r sine of theta. We know that cosine of negative pi over 4 is square root of 2 over 2. So that's 5 square roots of 2 over 2. And we know that sine of negative pi over 4 is negative square root of 2 over 2. So that's negative 5 square roots of 2 over 2. Therefore, point R is at 5 square roots of 2 over 2, comma, negative 5 square roots of 2 over 2. I only drew 4 circles, and that's okay because sometimes when I ask you to do a graph, there might be a point or two that go beyond the actual grid, but not far from it. So this is a good example of that. So it's good for you to see it. So the negative pi over 4 is about right here. Looking at that grid at the upper right corner right now. And unfortunately, that's where I wrote the Q. Oh well, I'll just graph it on top of it. Hopefully you'll be able to tell what I'm talking about. Let me make this a bold color so you can really see it. Okay, so since R is positive 5, I'm going to go out along the ray at negative pi over 4 and go 1 beyond the grid on that same ray, and that's where point R is. Then looking at the rectangular coordinates, 5 squared to 2 over 2 would be to the right, and negative 5 squared to 2 over 2 would be down, and so that seems like a logical position for that. And of course the graph isn't perfect, so you'll have to use your imagination a little bit there. But it's logical. As long as it's in the right quadrant and you're pretty close to the right value, you can probably be sure. What I'm asking you to check here is, intentionally I'm wanting you to check to make sure that it's close enough, that it's reasonable, because the problem will be you might be in the wrong quadrant, and that's the biggest consideration in my mind. Okay, so we finished those 3 examples and we plotted them. So let's practice what I was just talking about, giving alternate forms for coordinates of a point in polar. So it says give 3 other pairs of polar coordinates for the point P, which is 3 140 degrees. Okay, so the easiest ones will be ones where we keep the positive R and add a full 360 degrees to go all the way around the circle back to the same place. So 140 plus 360 is 500. So that one sounds good. Then instead of adding 360, if I keep the positive 3, I could subtract 360, and 140 minus 360 is negative 220 degrees. Okay. Now I'd like to make sure that we practice the negative R thing. And the negative R means that you go backwards, not along the ray that was given, but the one that's in the quadrant across from it. So like if this one is in quadrant 2, then I'm going to use a quadrant 4 angle that's 180 degrees away from this one, and use the negative R. So changing it to negative R, negative 3, I can add 180, and what would I get? 140 plus 180, it would be 320 degrees. And I'm going to do 4 just to give you an idea of the most common 4 to get that are the same. Or I could keep negative 3, and instead of adding 180 to 140 degrees, I could subtract 180, and that would be negative 40 degrees. And that's 4, not 3, but that's okay. That's 4 different correct answers, and of course that's just 4 of the many. Usually adding or subtracting a full cycle and keeping the R the same, or changing the sign on R and adding or subtracting 180 degrees. Those are the 2 major things that you would want to do. And of course if it's radians, that would be 2 pi for the first set and pi for the second one. Okay, this next one. Determine 2 pairs of polar coordinates for the point with rectangular coordinates negative 1, 1. Okay, so this is rectangular, so what they're telling me is that x is -1 and y is +1. Just a quick sketch, not even going to make very much of a big deal of it. I'm just going to kind of sketch it in the right spot so that I double check that my answer is correct. All right, so r squared is x squared plus y squared. And of course, 1 squared and -1 squared are each 1. You add those, you get 2. And here, when you take the square root of both sides, you'll get plus or minus the square root of 2. In the trig world, we did not put in the plus or minus because r was always, always, always positive. But in the polar world, r can be negative, so you will have to put in the plus or minus to account for both possibilities. So that's new, so you got to pay attention to it. Okay, then tangent of theta will be y, which is 1, over x, which is -1. And of course, if I plotted that, I'll even use the same grid I had over here. That's going to put me at that place. So I'm going to draw my little right triangle. And of course, this is -1, and that's 1, and that's square root of 2. And of course, when you think about that, you go, oh yeah, I know the reference angle here is a 45-degree angle. And so what is the angle that goes from the x-axis around to over there? Well, it's 135 degrees. So one of my answers could be 135 degrees. And that would be if I wanted to use the ray of 135 degrees, that means I'm using positive r. So one of my answers is positive square root of 2, comma, 135 degrees. And by the way, I just jumped to a conclusion that I should be using degrees. There was nothing in the directions to say whether that's true or not. So I could have been getting 3 pi over 4 instead. Anyway, we'll just stick with degrees, pretend like that's what was intended. If, however, I wanted, and this will happen, I'll ask for one answer where r is positive, one where r is negative. So let's use the negative square root of 2. Well, to do that, I can't use the ray that the point is on. I have to use the one that's actually in the quadrant opposite it, over the pole from it. So to get to that ray that's going through the fourth quadrant, I'd either have to add 180 or subtract 180. And so it's sort of, up to you what you want to do. I'm going to add 180, and I get 315 degrees. And make sure that you think that through, that if I were to go to 315 degrees, which is this ray right here, and with a negative r, that's going to make me go backwards. Square root of 2, which will put me at the point that I plotted originally. So that will work. So please double check this, because it's really easy to mess that up. All right. So now, not only can we convert individual points from one system to the other, we can also do whole sets of points. And sets of points are generally described with an equation like x squared plus y squared equals 16 is a set of points that will form a circle centered at the origin at radius 4. So equations can be converted from one form to the other. So we're going to take, at first, the ones we're going to work with are take a rectangular equation and convert it into a polar equation. All right, so let's see. Well, we know that y in polar is r sine theta. So I can take every y and just replace it with r sine theta. And x is r cosine theta. One thing I want to say about this is typically when we have y's and x's, we like to have it so that we can write it as a function, y equals something, or f of x equals something. So y equals a function of x is a pretty standard form that we sometimes like. But I do want to mention, like the one I said a second ago, this equation, if I were to solve for y, actually would not be one that I would readily think, oh, I know how to graph that. Y equals plus or minus the square root of 16 minus x squared. I don't think I would just know what that graph is until I practiced it a little bit. But this one, the standard form for this one, where y is not solved for, is actually acceptable. So ideally, we'll want to have y as a function of x, but if it's quadratic, a lot of times that's not what we do, and we put it in a form that is called a standard form for that figure so that we can easily graph it. Like this is the standard form of the equation of a circle that I have there. By the same token, we would like to solve these equations for r, so that r will be a function of theta. That's what we're going to want to do. However, there will be cases where you can't solve for r easily, or you just can't do it at all, and you leave it in terms of however it is. So if it's easy to solve for r, I want you to. Otherwise, sometimes you'll see me leaving it alone. Well, to solve this for r, I would add 3 to both sides and subtract r sine theta from both sides. That's to get all the r's together on one side of the equation or the other. Then, to get a single r out of that, I can factor r out from both of those terms. And then divide to solve for r. So in this particular case, r is 3 divided by cosine theta minus sine of theta. And believe it or not, that's actually a simplified answer, and that's as far as we're going to go with it. Okay. Now, if I asked you to graph this equation, r equals 3 over cosine theta minus sine theta, you would probably, if you don't have any kind of graphing technology, you're probably going to flip your lid a little bit because you're thinking, oh my gosh, how would I do that? When I'm going to tell you that when you're trying to graph a polar equation, technically what we're supposed to do is make up a bunch of thetas and calculate r values and plot a whole bunch of them until we see what's going on. For something this complicated, that's going to be a real pain. There are a couple of easy ones we could do though. These are nice. If I picked 0 and pi over 2 and pi and 3 pi over 2 and 2 pi, just to get us started on this whole idea of how do you graph. So let's see. Cosine of 0 is 1, minus sine of 0 is 0, 1 minus 0 is 1, 3 divided by 1 is 3. Pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. 0 minus 1 is negative 1. 3 over negative 1 is negative 3. Those are the easiest points in the world. The others will get a little bit more complicated. Not terribly, but a little bit more. Okay, cosine of pi is negative 1. Sine of pi is 0. Negative 1 minus 0 is negative 1. 3 divided by negative 1 is negative 3. 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. 0 minus negative 1 is positive 1. 3 divided by 1 is 3. And 2 pi. Cosine of 2 pi is 1 minus center of 2 pi is 0, so that's going to be 3. So if we were to graph this on a polar grid, the reason we're not seeing a lot of variability is because I picked really easy ones to plot. We're not going to see the definition of what this is supposed to look like from these points. We'd have to fill in, you know, like first quadrant angles and second quadrant angles and see what's going on. Anyhow, so when theta is 0, we're on the polar axis, and we go out to 3. Go out 3. At pi over 2, which is kind of like the positive y-axis, we're going to go -3, which is going to have us go down here 3. At pi, which is the negative x-axis, we're going to go to -3, which is not on this ray, but go backwards 3, and we get that point again. 3 pi over 2, 3 is that point down there again. 2 pi 3 is that point again. So like I said, this isn't a whole lot of information. But luckily for us, the rectangular equation here is the same set of points, just in a different description. Instead of using y's and x's, we have a description in terms of r and theta. Well, couldn't we graph that line? Because we know how to do that. Well, sure, its y-intercept is -3. Duh, there it is right there. And our slope is 1, so I could go up 1 over 1, up 1 over 1, up 1 over 1, which would take me to the other point I've already plotted, and then just draw the line through those points. So we were missing a whole bunch of data when I skipped a whole bunch of the angles. But that's the line you would get. And so graphing this one in particular from polar is not fun. So a lot of times to graph something in polar, the best thing to do would be to convert it to rectangular and see if we can graph it. There are some graphs, however, that in polar are way easier than the corresponding rectangular one. So sometimes we'll want to stay in polar, sometimes we'll want to stay in rectangular, and we'll just have to play it by ear as to which one is going to be better. So let's do another one. Let's move on to example B. Again, our directions are given the equation in rectangular, find the polar equation for it. So x squared plus y squared equals 4. So since we know that x squared plus y squared is r squared, we can just replace x squared plus y squared with r squared. If you wanted to, you could go take out the x, put r cosine theta in, and that would end up simplifying to be r squared cosine squared theta. Same thing with y, that would end up being r squared sine squared theta. Factor out the r squared. What's left would be cosine squared theta plus sine squared theta inside, which is 1. R squared times 1 would be r squared. This is faster. Okay, so can this be solved for r? Yeah. R is equal to plus or minus 2. Okay, so that would be, you have r equals a number. It's really easy to graph because that just means that you let theta take on every single angle, and for every single angle graph r equals 2, and that ends up being this circle. Now from a rectangular point of view, this makes sense because that's the equation of a circle whose center is the origin and whose radius is 2. Same graph. So this one's actually a toss-up as to what's easier. They're both easy, I guess you could say. Which is nice to know. Okay. So let's look at some that go the other way. Well, actually, not quite yet. Let's first look at graphing polar curves. And as we're going to see, sometimes trying to find a rectangular one for it is not going to be easy. And graphing it in this form is the best way to go, especially after you have a little bit of experience. So the first time you graph something, generally speaking, you want to make a whole bunch of ordered pairs and see what kind of shape it takes. And we could do that. Just make a set of ordered pairs and try theta equals 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6 pi, etc., and get a whole bunch of points with all the special angles we know, and plot all those and see what results. That would be fine. I'm going to teach you what I think is a better way. I'm going to write that equation with r being y and theta being x, because that's something we know how to graph, and we've done it recently within this course. And so I'm going to graph the good old y equals 3 sine of x graph, the rectangular version of that. Of course, with the number 1 in front of x, we know that the period is 2 pi divided by 1, which is 2 pi. And then we divide that by 4, and we get pi over 2, which means we want marks every pi over 2 on the x-axis. There's no phase shift. There's nothing subtracted from x within parentheses. There's no baseline change because there's nothing added to the function. So the baseline or middle points will be on the x-axis at 0. And our amplitude is 3. And so sine of 0 is 0. So the next mark over will be at the high value of 3, middle, low value of -3, middle, etc. And you can go this way, low, middle, high. And you can graph as many as you want. Well, instead of making a table of values, this is actually a graph full of values. These are all ordered pairs, x, y, that are the ordered pairs in the polar world, r theta. So, and so instead of making a table, I've made this graph that has an infinite number of points on it in lieu of making a table. So let me set up my grid. I'm looking at the y values of that graph. The largest y, which will end up being the r value, is 3. So I need to make sure I have at least 3 concentric circles. Sometimes I'll put an extra one on there just so that you can see some blank space that's not being used for graphing, but I wouldn't want to put 10 extra ones on there, especially if I'm doing this by hand. One extra doesn't hurt me too much. Anyhow, so let's start with the very first point we graphed in the xy version of this, 0, 0. So that means, and keep in mind, the theta is the x value and r is the y value. So kind of keep that in your head. So 0, 0, we're at angle 0, radius 0, so we're not moving from the pole at all. So that's actually a point on the pole itself. Then I'm going to skip to this point right here at pi over 2, 3. And at pi over 2, which is the angle here, I'll move out to 3. So move along the positive y-axis 1, 2, 3 and plot a point. Now the important thing is the infinite number of points between those need to be graphed. So as the angle changes from 0 to pi over 2, as we go through all of those angles, the radius values, the x and the y values over here are growing. So on our graph out over here, we're starting at radius 0, and as we rotate around the circle counterclockwise, the radius grows. And so I'm just going to represent that like this, that as we move around the angles, we're moving out further and further from the pole. So every one of these points, as theta increased, is further from the pole than the one before it. Okay, and I don't want to ruin that picture. but let me kind of show you what I'm talking about. So at this angle, and at this angle, and at this angle, and at this angle, and at this angle, etc., each one of those points, it's a little bit further out. I'm exaggerating so you can see it. Do you see how those are moving out? They're further away from the pole each time. That's what I'm trying to represent with that curve. Alrighty. Then at pi, which is the second mark over, 2 pi over 2 is pi, that's this point right here on the graph, we're back to 0. So at pi, which is this angle right here, we're back to the pole. What happened in between was those r values were decreasing in a symmetric way. So what I graphed in the first quadrant, I'm going to reverse that, make the r's get closer and closer and closer as we move around from pi over 2 to pi. And notice that this is creating, if I can do it without messing up too badly, sort of a symmetric graph there. Okay? So, that's what it sort of looks like. Now, in a second, when I change this into a rectangular equation, you're going to see that I didn't do that good of a job. In fact, up here, this one, that actually looks a whole lot closer to what it's supposed to look like. So unfortunately for me, and for you, I guess, that's not a very good picture. What I will say, I wish I could just erase the pink and not erase everything else I did, because all it does is undoes what I've done to a certain extent. And I don't want to undo everything I just did. A good pair of points to think about is anything that the trig answer is 1/2. So the sine of what angle gives you 1/2. These are good numbers to know. So I'm actually going to do a couple of points in a table, sort of. Normally I just do them in my head. So the sine of what gives you 1/2? Right, pi over 6. And so sine of pi over 6 is 1/2. 3 times 1/2 is 3/2. That's a point that's not that hard to get right. Another place where that happens is at 5 pi over 6. And sine of 5 pi over 6 is 1/2. 1/2 times 3 is 3/2. Okay, so I'm going to redo this graph over here to the right and get it a little bit better. That was kind of our first attempt, and the ideas we presented were good, but my execution wasn't very good. And this is going to help us get a little bit more clarity as to a couple more points that we can graph to help us get a really good graph compared to the one I drew. Okay, so let me try again. So 0 will be 0, pi over 2 will be 3, and pi will be 0. Oh, we didn't go any further than that. I wanted you to see that too, so I'll do that back here on the first one. So if I go to 3 pi over 2, which is this one right here, the answer is -3, which gives me that point right there again. And in between, as I was moving from pi to 3 pi over 2, notice that this graph is below the x-axis, which meant that r is negative. So in the third quadrant, I'm getting negative r's, which is giving me back all of these points in the first quadrant. And the same thing happens in the fourth quadrant. With those negative r's that you're going to get back all these points in the second quadrant. So it actually goes around the circle, around the shape there twice if you go all the way from 0 to 2 pi. By the time you go 0 to pi, you've actually completed all the way around once. And in Calculus 2, that's going to become important, that you know just what angle it takes to get around something exactly once and not go through it twice. Anyhow, back to our graphing. Pi over 6, which is about right here, should be out 1.5. And at 5 pi over 6, we should also be out 1.5. And so that's going to give me a little bit better idea of what this should look like. it looks something like that. That's actually not too bad. And those points that guided me really helped make that look a whole lot better than the first attempt. So, just for fun, it doesn't say to do this, but I think it's a good practice. Let's convert this rectangular equation into, I'm sorry, what am I saying? Let's convert our original polar equation and convert it to rectangular. Okay, so this is a polar equation, and that's what our graph is of. This one over here is pretty good. That's what our graph is of r equals 3 sine theta. So I have two tricks to go from polar to rectangular. Two tricks that are really helpful. And by the way, going from rectangular to polar, you'll reverse these tricks. I have two tricks. If it helps with whatever you're doing, you can square both sides of the equation. That's a good trick. The second trick that's really good is you can multiply both sides of the equation by r. And depending on what you have to begin with, one of these two tricks is usually useful in going from polar to rectangular. So in this one, if you notice the sine of theta that's there in this problem, it would be really nice if that were r sine theta, because then r sine theta could be replaced by y. So in this case, squaring both sides won't create an r in front of the sine of theta. So trick number one isn't really helpful here. But trick number two, if I multiply both sides by r, I would get r squared equals 3r sine theta. And then I know that r squared is equal to x squared plus y squared. And r sine theta is equal to y. And with x squared and y squared in the equation, with equal coefficients, I know this is a circle. So you notice that first graph that looks sort of more like an ellipse or a football or something, that was pretty bad. The second one's not bad at all. It actually looks circular. Anyway, what I'd want you to do if you were converting from polar to rectangular is go ahead and put that in the standard form for a circle. So I would want you to subtract 3y from both sides. We're going to need to complete the square for y, so leave a little bit of space there. Then, to complete the square, we take half of -3, which is -3/2, and square that, which is 9/4. So we're going to add 9/4 to both sides of this equation. And the completing of the square allows me to factor the y trinomial, and that becomes y minus 3/2 squared equals 9/4. And that is a circle. Its center is at 0.3/2. And its radius is 3/2. So let's look at the graph we have up there. Does that make sense? Does that jive with what, or concur with what we know? Well, where's the center of that circle? One of the points of that circle is at the pole. The other one on the positive y-axis is at 3. The center has to be halfway in between, so 0.3/2 makes sense. And that means that the radius 3/2 makes sense as well. So there you go. Doing all that, completing the square and all that, and then graphing, I think is a lot more work than if you just learn that whenever you have, and this is something I really pay attention to this, whenever you have r equals a constant like a sine theta, it's always going to graph as a circle. And one of the points that's on the graph is the pole, or you might think the origin. But one of the graphed points will be the pole. And the center will be on the y-axis. And the way you might remember that is that sine of theta is related to y, because y is equal to r sine theta. So when it's a sine theta in that position, the center's on the y-axis, and the a, if you look back at our equation 3, what about that circle is 3? Its diameter. So the diameter of that circle, not the radius, but the diameter of that circle is a. So that's kind of a nice thing to know. So if you see something that looks like that from now on and asks you to graph r equals 5 sine theta, piece of cake. By the way, while I'm saying that, I'm going to go ahead and tell you that if you have r equals a cosine theta, all of that's the same, except for, so that's first point's the same, second point's the same, except for the center will be on the what? Well, since it's cosine theta, and cosine is related to x, the center will be on the x-axis instead of the y-axis. And again, a is still the diameter. So where the center is the only change that you would make for a cosine theta as opposed to a sine theta. All right. So that was helpful. That was nice. So I know the directions say to plot a whole bunch of points that you've calculated in a table. I just don't like spending my time doing that, because I'm eventually going to tell you this is how I'm going to ask you to graph them anyway, unless, like if it's r equals 5 sine theta or r equals 7 cosine theta or whatever, you can now graph that using what I wrote over there to the right immediately. It's kind of like asking to graph y equals 2x plus 4. You can graph that without a table of values. Y-intercept's 4, go from the y-intercept up 2 over 1 to use your slope, plot a point, draw the line through those 2 points. At this stage of the game, you've done that enough where it's just easy and you're not having to make a table of values. And if it's r equals a sine theta or r equals a cosine theta, that's my expectation, is that you don't have to even do that graph up above like I did. That was the first time through, but now you should know how to make that work without having to even graph. Like I'm about to do now, I'm going to graph what this looks like in the rectangular world of x and y. Now for this one, the baseline is at y equals 2 because of that 2 that's added. So that's where our new baseline is. The graph its period is not changed from 2 pi because there's a 1 in front of x, and then 2 pi divided by 4 means we make a mark every pi over 2 on the x-axis. And the amplitude is 1. And there's no phase shift, so I think we're ready to go. At 0, cosine of 0 is 1. If you add 2, that means that you're going to be at the high point, 1 above the baseline, which is at the y value 3. The next point, instead of the high, the next one will be then middle, then low, amplitude 1, so 1 below the baseline, middle, high, middle, etc. The side, middle, low. And so this is an infinite number of ordered pairs, way better than a table for getting a bunch of values to plot. And looking at the y values, the biggest one again is 3. So when I go to draw this, I'm going to make sure I have at least r equals 3 available. And as I said earlier, I tend to like to go at least 1 beyond that. And you can tell hand drawing these circles is not perfect, so just do the best you can. All right, so At 0, the answer is 3, so go out to 3 there. Pi over 2 is 2, so at pi over 2, we're at 2. And in between those two places, r is just getting smaller, so the point is getting closer and closer and closer to the pole, like that, sort of. And if it's not perfect, don't worry. Until you know what the shape is supposed to look like, it's kind of hard to tell. It's a curve of some sort, and you're just guessing, which is fine. Okay. By the time you get to pi, which is right here, you should be down to 1. And of course, that whole time, the radius is still shrinking, going from 2 down to 1 away. Well, it's not very good. Let me try that again. Well, hold on. Didn't erase enough of it. Okay, there we go. Looks kind of like this. Oh, you're just going to have to excuse me. I'm not making that look great. Oh well. Pretty bumpy looking. It's supposed to be a nice smooth curve. Okay. Then by the time we get to 3 pi over 2, we should be back out to 2. And then by the time we get to 2 pi, we're back out to 3. So it goes like this. And of course, use your idea of symmetry. I mean, the graph is symmetrical, so it seems logical that this graph would have some symmetry involved as well. You may think that's a circle. It's not. This is a figure called a limacon. Don't speak French, so someone with a better accent can probably do that word better than I can. That little character there is a C with a little tail on it, and someone told me it's limacon. Anyway, pretend like my French accent is wonderful, and we'll go on. So let's see. Let's now graph r equals theta. Oh, before I do that, no, okay, I'll just do that one. It's fine. R equals theta. This one I'm going to make a table of values because the rectangular version of this isn't as helpful as you might think. So this will be fine. So I'm going to make up a value of theta and graph the corresponding r. So if theta is negative pi, r is negative pi. If theta is negative pi over 2, r is negative pi over 2. Because they're the same. When theta is 0, r is 0. Theta is pi over 2, r is pi over 2, etc. Seems like a silly waste of time, perhaps, because r and theta are always the same number. But the result of that is kind of interesting. Okay, so let's graph this one. At negative pi, which is right here, we're going to graph negative pi. So it's going to be over on the positive x-axis. Negative pi is about negative 3.14, so it's about right there. Negative pi over 2, which is right here, it's negative pi over 2. Half of 3.14 is 1.57, so about negative 1.57, which is about right here. Okay, and oh, negative, dang it, I graphed a positive. Negative 1.57 is going to be about right here. And 0, 0. So what's happening as we go from negative pi to negative pi over 2, we're getting values that are going like this. And then we're getting values that move towards 0. Like that. Then at pi over 2 here, we're out at pi over 2, which is the same place we just were. And then at pi, we'll be out at pi, which is 123.14. And then at 3 pi over 2, I'll be out at 3 pi over 2. I'm using my calculator for a second to get a decimal for that. So that's about 4.71. 1, 2, 3, 4.71. And at 2 pi, we'll be at 2 pi, which is about 6.28. 1, 2, 3, 4, 5, 6.28 is about right there. Oops. I'll pretend like that actually touches where it's supposed to. And so as theta gets bigger, r gets bigger. And so it's going to look like this. It's just going to go further out. As you go around, it's just going to get further and further out. This is not to scale. I'm just sort of guessing what it looks like. Anybody know what that's called? Anybody know yet? Yeah, it's a spiral. And if we were to go to negative infinity, so I was just now moving towards positive infinity, I'm going to make this part of the graph a different color so you can see where theta is negative. So this is this part of the spiral. Anyway, it continues going out like that forever and ever, spiraling out. So that's kind of interesting. That's what a spiral looks like. And I'll bet you cannot dream up a rectangular equation for r equals theta. I can't. I've never seen a spiral graph using using y's and x's. So that's a nice polar thing that really is best in polar. And that's going to happen sometimes. So let's graph another one. R equals 1 plus cosine theta. A whole lot of these figures, like that limicon and the spiral, those are ones that you would not try to do using x's and y's because they're not common graphs and not easy to reconcile with a y and x equation that you're used to. Okay, so to get my set of points, I'm going to graph the x and y version of this. The baseline is at 1. The marks on the x-axis are going to be every pi over 2. The amplitude is 1. The cosine of 0 is at the high point, which is 1 above the amplitude above the baseline, then middle, then low, middle, high, going this way, middle, low. So this informs us of a whole lot of points that we should be considering graphing. The highest y value on that graph is 2, so I can safely go out to about 3 and stop. That'll be plenty of information. Okay, so at angle 0, we're at 2. At angle pi over 2, we're at 1, and the radius decreased until you got there. At angle pi, you're actually in at 0, and the radius just decreased until you got there. Then at 3 pi over 2, you're out at 1. And so the radius increased out to there. And by 2 pi, you're out at 2, back to where we started. And anybody want to guess the name of this one? If I'd done a better job, you might have seen that that's kind of a heart-shaped thing. Think about cardiac arrest. This name will probably make more sense to you now. This is called a cardioid. Kind of a heart-shaped thing. Okay. And let's see what's next. R equals 3 cosine of 2 theta. So we can graph y equals 3 cosine of 2x to inform us of a whole bunch of ordered pairs that will be graphable on the polar grid once we get them done. The baseline is 0, so we're not going to move away from the x-axis vertically. The amplitude is 3. This time the period is 2 pi divided by 2, which is pi. And then the period divided by 4 is pi over 4. So I'm going to make a mark every pi over 4 on the x-axis. It's the first time we've done that in this lesson. It's changing it from not being pi over 2 to something else. So each mark here is a pi over 4 mark. Okay. See, cosine of 0 is 1, which is high value, so it'll be at the high value of 3 because the amplitude is 3. Next will be middle, low, 3 below the baseline, middle, high. You could keep going as far as you need to, and this way, middle, low. Okay, so you notice that I've been using the positive, well, 0 and positive values for graphing. I've graphed a little bit of stuff where x is negative, but I haven't really talked about them. I might actually do it this time. We'll see if I end up needing to do that. Sometimes you do. So I'm giving myself that opportunity. All right. And I'm giving myself that opportunity by graphing some negative x values, and if I need them, there they are. I think most of us are more comfortable dealing with positive theta than with negative theta, so that's usually enough information anyway, so this is fine. Okay, so at angle 0, I'm out at 3. By the time I get to pi over 4, which is right here, I'm at 0. So as I move from here to here around, the radius is decreasing, so it's shrinking, getting smaller and smaller and smaller, closer and closer to the pole until we actually get to the pole. And so the part I just graphed right there is between 0 and pi over 4. This part right there, where I put the check mark. Okay, from pi over 4 to pi over 2, well, let's just say at pi over 2, which is right here, at 2 pi over 4, pi over 2, we're at negative 3. So since it's negative, we're going to be graphing way down here on the opposite end of the line from the ray at pi over 2. And those values, as we move around from here to here, are negative values because these are below the x-axis, which means we're graphing in the opposite quadrant. And so we're graphing r's that are getting further and further from 0 until they get it to be, well, let me try that again. There is some symmetry involved here, so I'm trying to make it look right. Make it look like something else that we're about to see. Okay, so it looks about like that. This is supposed to be a smooth curve. If it looks a little bit jagged, that's my fault. Okay, by the time we get to 1, 2, third mark over, 3 pi over 4, which is right here, we should be back to 0. So as we go from here to here, we're doing these negative values. They're getting closer and closer to 0. So we're in the fourth quadrant with negative values because r is negative there, and we get that back to the pole. Okay, then from 1, 2, 3 pi over 4 to pi, it's back out to 3. Pi is right here, so out 1, 2, 3. And between the pole at 0 value, the r value is growing and growing and growing and growing until you get out to there. So that's that part. And then when the next mark, 1, 2, 3, 4, 5 pi over 4, which is right here, the last one I graphed to the right over there, we're back to 0. And so it comes back around like this. Okay. Now, and that gets us that part. So let's go to negative. So going to the left of the y-axis, between 0 and negative pi over 4, negative pi over 4 is down here someplace. The radius is decreasing. So our very first point we graphed was over here to the right on the y-axis. We're now going backwards. We're going to go from that point at 3 out on the positive x-axis in towards the pole at negative pi over 4. And that's going to look like this. Then by the time we get to 2 marks to the left, that's negative pi over 2, which is down here, negative pi over 2, we're supposed to be at negative 3. And so negative pi over 2 is down here. Negative r values will be on the other side. So that'll be here. And this will grow until we get out to there. And if I had one more graphed thing, it would get us to here. And that's a full rose curve. Now, one thing about rose curves that I'd like to mention is that if you have r equals a sine of n theta, or r equals a cosine of n theta, it's going to be a rose curve. If you notice, there are 4 petals on this particular one, and the length of the petal is 3. In other words, if you look at the petal, the distance along the axis of symmetry of that leaf, that distance for each one of those leaves is 3. So A is the length of the curve of each petal, and N governs how many petals you're going to have. If N is even, that means you're going to have twice as many petals. So here N was 2. That means 2 times 2, 4 is the number of petals we got. If N is odd, you get exactly that many petals. So if N is odd, you'll get N petals. So if N is 3, you get 3 petals. If N is 5, you get 5 petals. If N is 6, you'll get 12 petals. So listen for even or odd there. Okay, now that's a good place to stop because I'm at the end of this slide. So I'm going to stop there, and we'll continue in the next part.